Here's a schematic of a mass spectrometer. Here we have a mixture of ions. You can see they're represented by these different shapes and different colors. They will be accelerated here. Here's where the acceleration occurs, accelerating energy. So if these are positive ions, which is the way we did our mass spec, then this would be a negative plate here, and the positive ions get pulled toward the negative, positive on this side. So you have an electric field that accelerates the ions. They will gain a certain amount of energy. What that means is that the large mass, since K equals 1/2 mv squared, if energy is the same for each one, then a large mass means a slow velocity. So that's what they're illustrating here. The smallest particles have the highest velocity and therefore will reach the detector sooner. The large mass has a slow velocity and therefore takes longer to reach the detector. Most important things for you: if it didn't have a charge, it wouldn't get accelerated. So if we had here a square with no charge, it just sits there. It never gets to the detector at all. So only ions can be detected, and therefore we need to create ions out of neutral molecules. So we have to take a neutral and add something to it, question mark, so that it becomes a positive ion. Alright, here is an example mass spectrum. I'm starting first with what's called an isotope model. This is a molecule, benzyl cinnamate. It's not an ion. So by itself, it would not appear in the mass spectrum. It needs to have attached to it something that gives it a positive charge. The way things are done at UCI, the most likely adduct is a sodium ion, Na+. It could stick on to one of these oxygens here, and it just goes along for the ride. And if a sodium ion does attach to this, then we have a positively charged species that will fly in the mass spectrometer. Benzyl cinnamate alone is C16H14O2. You'll notice up here it has that plus a sodium. Benzyl cinnamate alone, molecular weight, you would say is 238 point something, plus a sodium gets you 261. Now, if you notice here the mass spectrum, the most common ion here has a mass of 261, but there are appreciable numbers that have a mass of 262 and a few that have a mass of 263. This is because the carbons are not all carbon-12. 1% of carbon on our planet is carbon-13, a heavier form. Poorly written. Carbon-13. Carbon with a mass of 13. Since there are quite a few carbons in here, 16 carbons, there's a reasonable chance that one of them will be carbon-13, and a pretty small chance that two of them will be carbon-13. So this is what is meant by an isotope model. These are all the same molecule. Just some of them have carbon-13, and some of them have two carbon-13s. If we did have other elements in here other than oxygen and hydrogen, we could also get some interesting information out of those isotopes. But here the only one of interest is the carbon. Could be heavier. Now let's look at the actual data. This is a mass spec we ran on Thursday. So this is real data. You can see that we do have these peaks at 261, 262, and 263 in the appropriate ratio, which gives very strong evidence that this sample did have indeed benzyl cinnamate as expected. These are the sodiated ions. This peak here is also easily identified. This is benzyl cinnamate plus the sodium to give it a charge, and something else. The something else would have a mass of 32. You can see 261 became 293. 32 grams per mole is almost certainly methanol. That is the solvent we used in the mass spectrometer. And it has a mass of 32 grams per mole. So this is benzyl cinnamate plus sodium plus methanol. You can think up here in my picture that the methanol was hydrogen bonded to the benzyl cinnamate. A sodium ion also was stuck on there. And that cluster, that group altogether, flew to the detector in the mass spectrometer. This peak here I have not been able to identify. It could be benzyl cinnamate plus something else to give it a higher mass. So in other words, an aggregate of molecules. It could be a different molecule altogether. It does look like an isotope pattern that suggests a large number of carbons, the ratio of the peaks here. So it's an organic molecule, but I don't know what it is. But the take-home message, we do have benzyl cinnamate here, and it's the highest peak that exists, so that's a good sign. And we may have something else. It's difficult to know what this peak actually means. Here's an example of a very complicated mass spectrum. And this was a synthesis in which the desired molecule is right here. It's an amine, and amines commonly pick up an H+ to become a positive ion. This molecule here is dicyclohexylurea, and this was an expected byproduct in the carbodiamide synthesis of this molecule. So in this case, I have some guesses as to what else might be in there. So I looked for the molecule, which has a mass of 143 grams per mole, and that's with the H+ attached, and I see there it is. So there's my molecule, number 1. I found this protonated dicyclohexylurea to have a mass of 225, and there it is. Then I have peak number 3 is identified as 2 of these. An APMA is 142, and if I had 2 of them, I'd have 284, and add a hydrogen and you get 285, and that's peak number 3 here. Then the complex of 1 of these molecules up here, and 1 of these molecules right here, and 1 hydrogen ion adds up to 367. You can see that peak is also there. And always there's these extra peaks that have a mass of 1 greater and 2 greater that illustrate the carbon-13, which are present at 1%. So that's, as you can see, it's a nice puzzle game, and if you have some idea of what's in there, you can often identify the peaks that appear in your mass spectrum. It's not really great at telling you relative quantities of things. It's semi-quantitative. The peak heights are semi-quantitative. You wouldn't want to use these as the basis of saying, oh, I have 50% of this molecule. But if the peak is big, that probably means there are a lot of those in your reaction mixture.